welcome. So, we are studying ADC and DAC, and in the last class we have seen this DAC circuit, okay, which is made up of this resistive network with resistances R to R, R to R, so on. Okay. So, that is why this is called a R to R ladder circuit. Okay. And so, let us now see another DAC, and this is actually you might have seen before, which we call the adder circuit. Okay. So, this is once again made up with an op amp, and there is a lot of similarity between this circuit and the previous circuit. Let us first see this circuit. Okay. So, this almost look like a inverting amplifier. So, the positive input is grounded and we have a negative feedback. And normally we have one input like this for inverting amplifier, and here we can connect say a voltage source, okay. So, you know, if this is R1, if this is R, then if we connect this, then VO is equal to, if this is Vi or call it Vref, then Vref multiplied by R by R1. So, this is the output for a normal inverting amplifier, but now we will modify this. What we will do is we will connect many inputs. So, this is another input, then we can have another input. Okay. If you want, you can have one more or as many as you want, and now you can connect this inputs to this Vref via switches. Okay. So, just let me call these switches as D0, D1, D2 and D3. Now, if you connect only one of them, and let me just give names. So, let me call this R0, R1, R2 and R3. So, these are the names of these resistances. Now, if you connect only one of them, say if you connect only D0, so then these are hanging or floating resistances, they have no effect in the circuit at all, and the output will simply be, if you connect only this, then the output will simply be R by R0 Vref. Similarly, if you connect only this, then the output will be this. Okay. If you connect only say D3, then the output will be this. But what will happen if you connect several of them together? Okay. So, then what will happen? Okay. So, let us see that. Okay. And the idea is this, let me first convince you that even if you connect several of them here, the principle of virtual sorting will work for this circuit, and therefore, these two will be at the same potential. Now, this is at 0 volt definitely. So, this will also be at 0 volt. Let me first convince you that the principle of virtual sorting holds true in this circuit. Even if a number of, that means even if many switches are closed together. Okay. Why is this so? The answer is as follows. You just realize that even if you connect all this or some of them here, then this is a positive potential, right? Okay. So, this is a positive potential with respect to ground, which will try to make this terminal positive, right. So, this is a positive potential, and so current will go like through these resistances, and it will try to make this potential positive, because this is positive, and you can connect all these only to a positive voltage. So, therefore, this will try to become positive or go up. Okay. So, it will try to go up or try to become positive. Now, if it is becoming positive, that means greater than 0 volt, then definitely the output will be negative, because we know for an op amp, if this input is at higher potential, then output goes towards the negative saturation or negative supply voltage. Therefore, the output here will decrease, and you know this is this will now affect through this resistance, this potential, and it will try to reduce this potential. Okay. So, we can actually write, I mean, if you know a bit of circuit theory or Millman's theorem, then we can immediately write that this potential, call this Vn, okay, this is Vn, this is Vp. So, Vn can be written as an average of this potential plus this potential plus this potential plus this plus this. This way you can write. So, we can write that Vn is equal to so V0. So, this will get a weight of 1 over R plus this potential is how much? This is same as V def. Okay. So, V def divided by R0 plus this is again V def, this is R1. So, V def divided by R1 plus similarly V def divided by R2 and plus V def divided by R3. This V def divided by R3. Now, this entire thing should get divided by the total weights 1 over R plus 1 over R0 plus 1 over R1 plus 1 over R2 plus 1 over R3. This is how you can write the voltage here. Okay. And this is called Millman's theorem, and this comes from simple circuit theory. Okay. Okay. So, you see in this formula, you see if you have V def positive, then Vn will try to be positive. Okay. If you increase V def, then this will also increase, right. And if this increases, so if this becomes positive, then Vo will become negative. So, this term will then become negative, and this negative term will try to make this negative. So, V def, if V def is positive, it will try to make this positive, and if Vo is negative, it will try to make it negative, and these two together will establish a balance where Vn will become exactly equal to 0. Okay. So, then the op amp will stay happily at that equilibrium. So, from virtual sorting we know that Vn will become 0, and if so, okay, if this is the case, then what can we write about VO? Okay, so VO, so let me call this current I, let me call this I0, this is I1, this is I2 and this is I3. So, then I can write the current I is sum of I0, I1, I2 and I3. Now, how much will be I0? I0 will be this is at Vref, this is at 0. So, divided by R0. So, Vref by R0. Similarly, this will be Vref by R1 plus Vref by R2 plus Vref by R3. This is because Vn is equal to 0, which implies this is I, okay. And from this we can write now VO is how much? This potential minus this drop. So, 0, so we can write VO is equal to 0 minus I R. So, this you can write as, now I is this much. So, this will get multiplied by R. So, therefore, we can write this as Vref, let me take Vref common. So, 1 over R0 plus 1 over R1 plus 1 over R2 plus 1 over R3, this is I. So, minus I times R, this is VO. Okay. So, this will be the output voltage provided all these switches are closed, right, then only these currents will flow. And if a switch is open, then say this is, if this switch is open, then this I1 will become 0. Okay. So, let me write that in this way. Let me call it, let me multiply this with D0. So, this is a binary variable or indicator variable, which can take the value of 0 or 1. Vref, sorry, D0 equal to 0 means that this switch is open, therefore, this current I0 will be 0. Similarly, if I multiply here with D1, now D1 0 means this switch is open, therefore, this current will be 0. Similarly, here I will write D2 and D3. This is exactly what we did in our last class also. So, let me write it that D0 equal to 0 implies switch D0 is on or closed. So, the current can flow, and this is equal to 1, sorry, this is equal to 1 means this is on, and this is equal to 0 means that the switch is off or open, right. So, this is the now expression for V0, and I will copy this. Okay. Now, what I will do, I will choose say R3 is equal to R by 2, R2 no, not R by 2, 2R, R2 equal to 4R and R1 equal to 8R and R0 equal to 16R. So, therefore, what we will have is this V0 is equal to minus Vref, here in place of 1 by R0, let me take this R inside. So, I will have R divided by R0 is 16R, okay, plus R by this will become 8R plus r by 4r plus r by 2r. So, this you can also write as this r they cancel. So, we have 1 by 16 plus r, okay, plus 1 by 8 plus 1 by 4 plus 1 by 2. I have done a small mistake. The mistake is that when I have multiplied this d0, d1 etc. To actually indicate whether this current I0, I1 they flow or not. So, I should also write those variables here in the expression of the voltage d0, d1, d2 and d3. So, d0 actually indicates whether the current I0 is flowing at all or not. Okay. So, this I have to put these variables d0, d1, d2, d3 etc. So, I forgot to put that. Let me put this again here d0, d1, d2, d3 and so therefore, I will have this d0, d1, d2, d3, d0, d1, d2, d3. Okay. So, now you see that this is actually like this is actually a DAC, right, because okay, let me write it this way, minus V ref by 16, okay, and then I can write this is equal to d0 plus 2 d1 plus 4 d2 plus this will be 0 2 4 8 d3. So, you see, okay, further I write this as V ref by 16 d0 plus, okay, let me write from the right side. So, this I will write 2 cube d3 plus 2 square d2 plus 2 to the power 1 d1 plus d0, 2 to the power, or you can write 2 to the power 0 d0. So, now you see that this is actually minus V ref by 16 multiplied by a binary number represented by the states of the switches D3, D2, D1 and D0. Example, for example, if we choose D3 equal to 0, D2 equal to 0, D1 equal to 0 and only D0 is equal to 1, then V output will be minus V ref by 16 into 1. Similarly, you can take another example. So, let me take D3 equal to 1, D2 equal to 0, D1 equal to 1 and D0 equal to 0. Now, this number 1 0 1 0 1 0 1 0 is equal to this is 10, decimal 10. So, therefore, V output will be minus V ref by 16 into 10. Okay. And this term over here, you can call this is the resolution of the DAC. Okay. So, this is how it works, and right. Okay. Now, let me just give you a small homework, and the homework is prove this formula. Which formula? This formula. Prove this formula. I will just give you a clue The clue is you apply the KCL, Kirchhoff's current law, at this point. Okay. So, you can write that the sum of I 0 plus I 1 plus I 2 plus or minus I, okay, I 0 plus I 1 plus I 2 minus I, or plus I if you take I in this direction. Okay. So, sum of these currents then should be 0 at this point, and then I 0 can be written as this voltage divided by R 0, this current can be written as this voltage divided by R 1. So, from that you can actually write that this V ref by R 0 plus V ref by R 1 plus V ref by R 2, V ref by R 3, and finally V 0 divided by I, plus if you take I in this direction, this should be equal to 0, sorry, this is R, this should be equal to 0, and from this, starting from this condition, you just prove what will be the okay, I have made a mistake. This will be V ref minus V n by R 0. Let me write it again. V ref minus V n by R 0. So, this is this current. Okay. V n the value is unknown. Then here you can write this as V ref minus V n divided by R 1. This is this current, and similarly plus these two currents you have to add, and then this current, how much will be this? This will be V o minus V n, okay, V o minus V n divided by R. So, this total sum should be 0, and from this you find the expression of V n in terms of V ref and V o. Okay. So, please do this homework. This is very easy. If you need any help, we will help you through our forum. Okay. Now, let us just see a small similarity between this circuit and the previous circuit. Okay. So, this is important, I mean not this is very interesting. You just see in both these circuits the output voltage, okay, here the output voltage is how much? RF times this current minus of that, it is written here. Okay. So, because this is at 0 potential, virtual sorting works here. So, this is at 0 potential. So, output will be same as this drop, which is this current multiplied by this resistance. And how much is this current? This current is this plus this plus this plus this, provided whether these switches are on or not. Okay. So, basically we add up these currents, and we have taken a network such that these currents are in I mean binary order, like this is I ref by 2, this is half of this is half of this, and this is even half of this. So, this is like half unit, 1/4 unit, 1/8 unit, 1/16 unit, and these currents get added, and therefore, we multiply the total current with this RF. So, basically we add currents, and these currents are in binary ratios. Similarly, in this circuit also you see if you close these switches, okay, then these currents they are written here. You see they will be in binary ratios when we choose R 0, R 1, R 2, R 3 in this way. one is, so this is double of this, this is double of this, this is double of this. So therefore these currents you see, basically these are nothing but I0, I1, I2 and I3. So these are like half of this, and this is half of this, and so on. And then we add these currents. So all these currents get added, and then they together flow through this, and this voltage is once again, okay, this I can write, is once again minus I is in this direction, times the R, this resistance. So you see both these circuits are quite similar. This also adds currents, this also adds currents. Here also I need to just have produce currents in binary ratios, in the ratio of like 1:2:3:4. Similarly, here also I have currents added, and the currents are in ratios 1:2:3:4 here. That is the principle. Okay. So that's all about DAC in this course. I will finish this class after a bit of discussion on ADC, a new type of ADC, flash type. Okay. So previously we have seen what successive approximation type, or linear or digital ramp type, etc. So, we have studied this type as a voltmeter, and then I have said that a voltmeter can also be thought, I mean a digital voltmeter can also be thought as a analog to digital converter, right. So, that is why I said we need not study ADC circuits separately once we have studied these types of digital voltmeters. Okay. Now, this is more commonly used, this is sorry not this one, this one, this is not used because you know this is faster, this is slower. Okay. Although the mechanism is simple, the mechanism is what? So, mechanism is compare the input voltage with variable known reference voltages one by one. So, you know we generate different level of reference voltages using a ramp generator, which keeps on increasing, and we compare those voltages with the input voltage. At the moment we get these two voltages, ramp and the input, close to each other, the comparison stops, and that is the measurement of the input. So, that is the mechanism in very briefly. This is not used much as compared to this one. Okay. But you just see that observe these methods needs some time to measure or convert the input voltage. Why? Because we compare with different voltages one by one, different reference or known voltages one by one, one at a time, one by one. Okay. So, therefore, it takes some time, because we compare every time one input, the one reference voltage with the input, and if they do not match, then we change the reference voltage. So, it takes some time, okay. And depending on how many comparisons we do, those many clock cycles we need, right. And in this case we need n comparisons, n measurements, if it is a n bit ADC, and in this case we need 2 to the power n comparisons. So, this is slower, but anyway this also needs some time, a finite time, n number of comparisons. So, it will take n number of cycles. Now, flash type ADC is an ADC which will do multiple comparisons at once. So, it is like a parallel processing, whereas these are like serial processing. Okay. So, flash type ADC does many comparisons at once. Okay. This is the beauty of this flash type ADC. So, this will be even faster. So, it will take no time. Okay. So, it is a almost instantaneous measurement. Okay. Now, let us see how it works. It is very simple. Suppose I want to measure voltage between 0 to 8 volt, okay, for example, and say the resolution of the measurement is 1 volt. Okay. So, then we can take a 3 bit ADC, 2 to the power 3 is 8. Okay. Then I can measure 0 to 7 volt, okay, not 8. Okay. So, let us say V resolution is the resolution of conversion, and say we have n bit ADC. So, this implies measurable range is how much? Okay, this is a small quiz question that I can ask you. So, the measurable range is how much? This will be 0 volt to 2 to the power n, and this multiplied by V days. Okay. So, if I take n equal to 3, this will be 0 volt to this minus 1. V days. So, this is the range. So, this will be 0 to 7 volt. Okay. Now, let us see the circuit. So, we will just take a potential divider, a long potential divider like this, 1, 2, 3, 4, 5, 6, 7, 8. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Here I will connect this to 0 volt. This side I will connect it to 2 to the power n multiplied by V resolution, this voltage, okay, and let me call this as V reference voltage, which is 2 to the power n multiplied by V resolution of measurement. Okay. So, so this is the voltage at this point, and so what will be the voltage here in these points? So, this will be 0 volt, and this is, say, n is 3. So, this is 8 times V res, and it will get divided by 1, 2, 3, 4, 5, 6, 7, 8 resistances, all equal value, call them R, 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 R. So, this voltage will therefore be 1 over 8 times this total voltage. So, this will be V resolution, this will be same as 2 V resolution, this is 3 V resolution, this is 4 V resolution, 5, 6, 7 V resolution, and this is 8 V resolution. So, these are the 8 different voltage levels that I have generated. Now, what I will do, I will take comparators 1, 2, 3, 4 and so on, and I will connect this. So, let me put plus minus, plus minus, plus minus, plus minus. Okay. Let me connect this to this minus input, let me connect this to this minus input, let me connect this to this minus input, this to this minus input, and so on. Now, the plus sides are here. Let me sort this all pluses together. Okay, we will have many comparators, and let me put the last comparator. Here plus minus. So, 1, 2, 3, 4, 5, 6, 7, 8. Okay, before that we can have this one more plus minus, and all these plus inputs are sorted together. Okay, and these are the outputs. Now, this output will be high when if this input, this dead input is higher than 0 volt. Similarly, this will be high if this red input is higher than this black one, which is V res. Let me give the unknown input V in here. So, this is the input voltage to this ADC circuit which comes here. Therefore, this will tell me, so this will be high if V in greater than 0 volt, else low. Similarly, this will be high if V in greater than V resolution, otherwise it will be low. Similarly, this will be high if V in is greater than how much? This is 4, this is greater than 4V resolution. Similarly, this way here I can write this will be high if V in is greater than 7V resolution, right. So, this comparators tells me whether the input voltage is above 0 volt, above V resolution, above twice V resolution, or thrice V resolution, or 4 times V resolution, or 7 times V resolution, so on. So, you see all these comparators work together. So, therefore, we do many comparisons simultaneously, unlike in a say successive approximation or digital ramp type ADC, where we had only one comparator. Therefore, we could ask one question at a time and we had to ask all the questions sequentially, but here we have so many comparators. So, we can ask many questions simultaneously together, okay. And therefore, what we will do, we will get these answers. So, now let me connect it to a digital circuit, digital or logic circuit, which has these 8 inputs, okay, and this can be high or low, okay. So, this will be high if the input is higher than V raise, or low if input is higher than 7 V lower than 7 V raise, okay. So, these are the inputs to this digital circuit. You can call these inputs as what do you want to call x1, x2, or you may call it this way x0, x1, this is x7, this is x6, and so on. And it will have 3 outputs. Call this as y0, y1, and y2. Okay. Now, you would have to design this digital circuit. This is okay. Let me put this as a homework. Design the digital circuit such that these 3 numbers represent the digital equivalent of this input voltages of the this input voltage. Okay. So, what you have to do? You have to basically write a truth table. Okay. Let me do it on the next page. Okay. So, you have to write a truth table. So, where the inputs are x0, x1, x2, x3, x4, x5, x6, and x7. These are inputs, and output is y0, y1, y2, and these are the outputs. Now, say if the input is this is okay. I would write it the other way. Two 1 0, x7, x6, x5, x4, x3, x2, x1, x0. And say if the input is that x0 is 1, rest of these are 0. Okay. So, this means So, this actually means that V in input voltage is above 0 volt, greater than 0 volt, but V in is less than this V resolution. Now, if that is the case, so this will be low, and of course, this will also be low, because if the input is lower than V days, it is also lower than 4 V days, 5 V days, etc. So, they all will be low. Okay. So, this is the, if this is the pattern, okay, which means V in is greater than 0 and less than V days, you may like to represent the output as what? So, 0 0 0, this is one choice. You may also choose it to call this equal to 1. So, we have two choices. This is a choice that you have to make. Okay. So, I mean, if V in is less than V days, whether you call that as 0 volt or 1 volt, anyway this is an approximation. So, whether you call it 0 volt or 1 volt, that choice you have to make. So, suppose we make this choice, this is 1, then okay, then in the case when this is the situation, this is not possible, right? This input is, I mean, this pattern is not possible, because here it wants 1 means that this is high. This is high means input is higher than V days, and if the input is higher than V days, it is definitely higher than 0 volt. So, this is not possible. You just see this is not possible. So, a valid input will be this. Now, this you can call, okay, I will call this is equivalent to 2 unit 0 1 0, okay, because here V in is greater than V days, okay, that is why this is high, but this V in is less than 2 V days. So, V in lies between V days and 2. So, let me write it this way. V in lies between V days and 2 V days, and I will call, okay, this is approximately equal to 2. Okay. So, this way you can complete this truth table, okay, and then you can design the logical circuits for these 3 functions y0, y1 and y2. Okay. So, that's that I assume that you have already done some courses on digital electronics. So, you can do this yourself, and I am not going into it. That is a homework. Okay. So, let me now, the final thing I will say, this is a trivial thing. You can also skip this if you if you would like. Say input output curve or graph for an ADC. Okay. So, let us take this, let us take a 4-bit ADC. Okay. So, 4-bit ADC means if the resolution of the measurement is V days, if this is V days, so this is input, this is output, okay, input in volts or voltage, the resolution is V days, this is 0, 1, 2 V days, 3 V days, okay, 4 V days, and we can measure only in this range 0 to 3 or okay 0 to 4 somewhat. Now how should the output look like? The output, it's not going to be a continuous voltage or an analog voltage like the input. So, this will be a binary number. Okay. So, so this is a sorry I have, let me take a 2-bit ADC. Okay. I have taken a 2-bit ADC for simplicity, okay, which can represent only 4 levels. Okay. So, then the output can take these 4 values 0 0, 0 1, 1 0 and 1 1. So, these are the 4 possible values. So, you can, so this is like 0, this is like 1, this is 2, this is 3, and okay. Now, okay, let me ask you, if the input is 0 volt, say if the input is 0 volt, so input is here, what should be the output? Okay. If the input is here, what should be the output? A natural answer, normal answer is, okay, input is 0, output should be 0. Okay. So, you may choose that the output is 0 in this part. So, this is one point, and say if the input is equal to V days, what should be the output? Okay, and the natural answer is the output should be 1, because the input is equal to 1 times V days. So, this should be another point on the input output graph. Similarly, if the input is this, what output do you expect? Okay, you may say I want the output to be 2. And if this is equal, if the input is 3 volt, then you may want the output to be 3. Okay, so we have got 4 points on this graph. Now, I cannot just join a straight line like this, because if I do so, the output cannot pass through these points, because output cannot take this value of half, output can take only value 0 or 1. Okay. So, but the input can take this value, say the input is half times V days, what should be the output? If input equal to V days by 2, then output is equal to what? You cannot say the output is half, you have to say either it is 0 or 1. So, we have 2 choices. Okay. So, we have 2 choices. Choice number 1, okay, I will say the output is 0 0. Choice now, if this is choice number 2, I will say the output is this. Say if we choose this, if we choose this is the case, then okay, then that means here also the output will be 0. Now, then let me ask, if the input is equal to 0.9 V days, which is here at this point, slightly before V days, then output is how much? you cannot say the output is 0.9, you have to say either the output is 0 or 1. So, we have again two choices. You can say this is one choice, you can say this is another choice. I mean, this is what you can demand, this is your choice, you can demand this. Okay? Accordingly, we will make the circuits, we will modify the circuits, right. So, we have two choices, say I choose this one. Okay, fine. Now, that means I am clear that for this input also I want the output to be 0. So, which naturally tells me that okay, for any input below Vdes, V resolution, the output should be 0. So, the output stays at 0 here. Only if the input is equal to Vdes, then the output will go here. Then similarly, I can extend this idea. So, I can demand okay, at this value when the input is between 1 and 2 times Vdes, the output should be 0. This is my demand, I want this to happen. Okay. This is one choice. So, the output curve will look like this. And then okay, let me just draw it with a dotted line. So, this is a step jump, this is a rapid jump. So, any input below Vdes will give me output equal to 0, and slightly a higher voltage greater than Vdes will give me output equal to 1 until the Vdes goes to twice, sorry, input goes to twice Vdes. Okay. And then at this point the output will increase, and then in this region I demand the output to be equal to 2. Similarly, in this region I demand the output to be equal to 3. Okay. So, this is then the input output curve. Anything above this will also give me 3 naturally, because we cannot, I mean this is a normal expectation, I should expect like this, because this there is we cannot represent output equal to 4. So, this is one choice, but similarly we can have another choice for the input output curve. How? So, let us go back. So, here we asked the question, if the input is Vdes by 2, what should be the output? That means, when the input is here, what should be the output? We have chosen the output to be 0, but suppose we had chosen the output to be this one, that for the input equal to half times the resolution, output should be 1. So, then I would have a point here on the input output characteristic. I can also ask if input equal to 0.1 Vdes, output equal to how much? Okay. I choose the output should be equal to 1. This is 0.1, that means here, so between these two ranges. So, I can choose either 1 or 0, I choose 1, this is another choice. I could have also chosen this, but this is the choice that I make, and if I make this choice, okay, then this is another point on the input output characteristic. So, in this way I can choose, I can demand that for any input in this range between 0 and 1 unit, 1 V resolution, the output should be 1. Then I will demand this is the input output characteristic. Similarly, I will demand for any input in this range, output should be 1. Okay. So, this is my choice. So, here at this value the output will jump rapidly, slightly less than 1 unit will give me 0, slightly above 1 unit will give me 1. This is another choice. Similarly, I choose the output to be in this, if the input is in this range, output to be equal to this. So, this is another input output characteristic, and then definitely this will also continue like this. Okay. So, this is another choice. Okay. Call it choice 2, call it choice 1. Now, which choice is better? Let us ask, which choice is better? If we can if I tell you that this choice is better, then I will design my ADC circuit in a way such that for this input any value within this output is this. I will design this circuit so that we have this characteristic. If I can justify that this is a better characteristic, then I have to design the circuit so that this characteristic is obtained. So, that is a different question. Okay. So, depending on which characteristic I want, I have to design the circuit accordingly. That is a different question, absolutely different question. Let me just tell you briefly. For example, we have seen this flash type ADC. Okay. And then you see we have told that we have two choices for this input. This means this is 1, everything else is 0, means input is between these two ranges, 0 and Vres. Okay. Here, and we have chosen the output to be equal to 1. We could have also chosen the output to be equal to this, 0. Okay. The input is between 0 and 1 unit. So, you see like this. So, this is the red one. So, for this input we can choose the output to be 0. So, this is, and similarly let me write this in blue ink. This is another choice I can make. So, these are two choices. Two choices to design the truth table. Now, whichever choice you make it consistently for all other values here, and then you can design the logical circuit accordingly. So, you can design it, that is not an issue, it is absolutely possible. But now, which choice is better? Okay. So, for that let us estimate the error. What do we mean by this error? We mean this, that ideally this is a discrete output. So, output cannot take values between 0 and 1, it cannot take value half, 0.6, 0.4 anything. But had that been possible, we would have demanded that for this input half, output is half. That is not possible, but if that was possible, if the output was continuous analog, we would have desired this as the output, right. So, this is the best input output characteristic, which is not realizable with a discrete output. So, this is the best input output characteristic, but not realizable. But this is the best one. So, we would like to stick as close to this as possible, and if we deviate from this, that will be our error. For example, you see when the so let us first consider the red curve. So consider the red curve. Okay. So, for this input, for let us see how much is the error. Okay. First, let us consider the input is equal to V raise times 0.5, which is here. Then how much is the error? We will define the error to be the output, which is 0, versus and the difference from this to this black curve, which is the best output, which is not possible. So, here the value is half. So, this value is half, okay, and we would like the output to be half, but that is not possible. So, we are choosing the output to be 0. So, therefore, this is the error. This is the error. Okay. So, input, if the input is this, then the output is 0 and the error is how much? So, we will say the error is half unit, because we would expect the output to be half. Okay. So, let me write best output, which is not possible, should be half, but our actual output is 0. So, the error is 0 minus half is half. Similarly, let us consider this point here, when the input is equal to 0.9 V days, then the best output will be 0.9 here on this black curve, but actual output is how much? Is 0. So, error is 0.9. So, this is the error. Now, what is the maximum error in this way we can have? The maximum error that we can have this is almost equal to, okay. So, this is almost equal to 1 times almost equal to 1 unit, okay, when input is say equal to 0.99999 V days here, then this will be the 1 unit error. So, this is the maximum error. Okay. So, now similarly, let us so this is the error. So, similarly at this input, this is the error, at this value of input, this is the error, at this value of input, this is the error. So, this is the error, and the maximum error is 1 unit for the red curve. Okay. Now, so similarly let us consider what happens for the blue curve. Say if the input is half 0.5 times V raise, then the error will be how much? This much, half unit. Once again, I am doing it quickly. because I think now you have understood this. Okay. And similarly, if the input is say very close to 0, 0.1 times V raise, then the error is how much? 0.9, 0.9 unit. And so, what will be the maximum error? This is almost equal to 1 unit, say when input is equal to 0.000001 V raise. So, at this point we will have an error of 1. This. Similarly, these are all the errors at different inputs. So, this is the maximum error, this is the maximum error, this here is the minimum error, here is the minimum error, and so on. Okay. So, for both these curves, you see, for both red and blue, the maximum error is 1 unit. So, both these curves are similar. So, we ask the question which choice is better, but we see both are similar. Now, I am going to give you another choice, choice 3, which I will say is better than both this, and which is going to be the best choice. Okay. So, the best choice will be this. Okay. So, I will demand that for input between 0 and half V raise, the output should be 0. So, that curve will be 0 here, and for input between above half and less than 1, the output will be here, because above half, above 0.5 is close to 1. So, I will demand the output to be 1 here, and we will have a step jump here. Similarly, if the input is between 1 and 2 of the resolution, then if it is less than 1.5 on this side, I will demand the output to be 1, because less than 1.5 is close to 1 compared to 2, and similarly, if the input is above 1.5, I will demand the output to be here, and I will have a step jump here. Similarly, here I will divide it into halves. If it is less than 2.5, output should be 2. If it is above 2.5, output should be 3. This is the next curve. Okay. So, this is, I will call this is the best choice, this green curve. Why? Best choice is the green curve. Why is it best? Let us see error. How much is the error? So, error at any point is the deviation of this curve from this black curve, which is like this, and here it is like this. How much error can we have at max? So, the maximum error is this height. This is the maximum error, right? And this is how much? Half unit. Okay. So, the maximum error is half unit. Okay. So, that is why this is best. Let me just, if you haven't followed this, let me just also take an example. Say input equal to say 0.49 Vres, okay. Then best output is 0.49 according to this black curve, but the actual output will be 0. At this point the output is 0. So, the error is equal to 0.49. Similarly, if input is 0.51, best output which is not obtainable is 0.51, actual output by choice is made to 1. So, the error is again, you see the difference between these two is 0.49. So, the maximum error we can have is definitely half unit. So, this is another possible characteristic. So, now this is the best choice. This if you are a computer scientist or from a computer science background, you will write this as a round function. So, this round offs the input in a way. This blue one you will write this as ceil function, and this red one you will write this as a floor function. If you are a computer scientist or a mathematician, this is how you may like to write it. Okay. So, now let me just finish this video. So, these are the different characteristic curves you can demand, you can like to have. This is your choice which one you like, and the next task is to design the circuit accordingly. We have already seen in flash type of ADC how you can choose between two possible characteristics, the red one and the blue one. And if you, okay, this is a homework, how you can realize the green curve, the best curve in a flash type ADC. You simply have to adjust in the potential divider, you have to add a offset resistance, so that all the threshold voltages are not 0, 1, 2 Vres, but half, 1.5, 2.5, 3.5 Vres. You have to just adjust this in the potential divider that we had R. You have to adjust it slightly. This is a homework. Do it, please. This will be very nice and fun. Thank you.